Readers from Chinese Academy of Science, Nanjing University, and North Carolina State University. We live in a sparse world. Sparse matrix vector multiplication, we call SpMV, is one of the most important and fundamental sparse kernels. Because of the diversity of metric sparsity patterns, each of which requires a different tailored program design, auto-tuning is a very important way to improve SpMV performance. However, modern SpMV auto-tuners still face a fundamental dilemma, balancing performance and the search overhead. Current auto-tuners can be divided into two categories: template-based and template-free approaches. This slide shows template-based auto-tuners. The left side, format selector selects from predefined candidates programs for the input. The right side, compiler-based auto-tuner, includes predefined primitive combinations and tunes the inner parameters. Both the candidate programs and primitive combinations act as templates, which limits the performance potential. To overcome the limitation of template-based methods, we propose AlphaSparse in 2022. It imitates human expert by breaking down the manual program design process into sequential steps. Each step is defined as an operator. As you can see in the diagram, by combining just 4 operators, AlphaSparse can generate 3 fundamental SpMV programs from scratch. In terms of these example operators, the operator compress removes zeros from the matrix. The operator row blocking blocks the compressed matrix in row direction and map each part to a different computing unit. So then we can get a CSR format. The operator column blocking further block the matrix in column direction, and we can get COO format. Operator padding adds zeros to rows, so then we can get the ELL format. Today, AlphaSparse has included 24 operators. They construct a huge template-free space, even including lots of potential new SpMV programs not covered by existing researches. So that it provides higher performance than template-based methods. However, the huge space comes with a huge auto-tuning overhead. Our goal is to develop an auto-tuner that achieves high SpMV performance and minimal search overhead. So we adopt search space of AlphaSparse and use machine learning technology to accelerate search process. Using the machine learning to accelerate sparse auto-tuning is not a new idea. One common approach is matrix classification. This methodology first extracts features from input matrices and uses the ML classifying model to map the input matrix to a specific category corresponding to a candidate program. It is lightweight, but is applicable only to format selector and unsuitable for template-free auto-tuning. To accelerate template-free auto-tuner like AlphaSparse, the traditional machine learning approach relies on a cost model. In the perspective of AlphaSparse, here is an example search space where every single point represents a specific operator combination, and we navigate this search space to find the suitable operator combinations for a specific matrix. The cost model is used to predict the performance of enumerated operator combinations and move towards the best design step by step. This requires evaluating a massive number of candidates. As a result, the overall search overhead remains high, time-consuming. This is the starting point of our thinking. But this brings us a fundamental question: why we must search? Can we just skip the iterative process and directly generate the best possible solution? This called for a new sparse auto-tuning methodology. bypass the iterative search by one-pass program generation. We reformulate auto-tuning as a sequential decision-making process. It predicts and appends alpha sparse operators one by one directly, construct the final SpMV program. Therefore, we cast our auto-tuning process as an instance of behavior cloning problem. Behavior cloning has been widely adopted in expert systems, including autonomous driving and game playing AI. It relies on three key concepts. First is the action, which denotes an expert's decision, like steering or braking in auto driving. Second is the action sequence, which is the series of actions required to complete a task. Third is the state, which captures the real-time context guiding each action prediction. In this way, we can map SpMV from auto-tuning concepts onto this behavior cloning framework. Actions correspond to alpha sparse operators. Action sequence respond complete SpMV program designs. And the state is the partially constructed program. By appending actions step by step, we can directly generate the optimal SpMV programs without any iterative searching. I think this methodology can not only accelerate SpMV autotuners like alpha sparse, but also other compilers who need to find the best pass combinations. However, this one-pass methodology introduced two new challenges. The challenge one is that we must shift to a real-time state-centric prediction. By construct, existing sparse autotuners are input-centric. They rely on static input information, which quickly becomes outdated as actions modify the matrix during iteration. To solve this, we used intermediate representation from our program generation method to serve as the dynamic state. Challenge two is the massive overhead of offline data collection. Because our model generates the optimal action sequence for each matrix, our training set must contain the absolute optimal sequence for every single matrix. Finding this is extremely time-consuming. Existing autotuners do not need to solve this problem, either because their search space are very small or because their dataset doesn't require the absolute optimal sequence for matrices. To solve this problem, we introduce a self-training mechanism. The background of our paper originates from our two previous works, corresponding to the action and state spaces. This slide briefly introduces the action space, which is inherited from alpha sparse. Some of actions include tunable parameters. These actions allow us to change the matrix layout, map data to parallel processing units, choose reduction algorithms, and configure the kernel. If you're interested in them, please refer to alpha sparse paper. The intermediate representation of our code generator method is also introduced in our previous work, SRSparse. It has two parts, which is the middle layer transformed by actions to generate SpMV programs. The first part is matrix metadata set, which records matrix information, including layout, data mapping, and the extralarity data for reduction algorithms. Actions sequentially transform its content, and the metadata array used in kernel will form the final sparse format. The second part is the kernel skeleton. It maintains the code structure, including the position of loop structure and reduction algorithms. Actions progressively fill code into this skeleton to form the final code implementation. Now that we have introduced action and state, let's see how they came together to form the workload of online inference phase. First, the input matrix initialize the states. Next, ML models predict the next action based on the current state. Then, this predicts actions is applied to update the state. The loop repeats until the design is completed. Ultimately, the customized program is generated in a one-pass fashion. The key of online inference is IR-centric feature engineering. State features are extracted from the metadata arrays and the semi-completed kernel code. Unlike existing sparse autotuners that extract features from two-dimensional matrices, we need to extract features from one-dimensional metadata array. This is a difference. Thus, we introduce a fundamental operation called SIGStat. It applies a 1D difference filter to the sequential data and then compress the filter output into several matrices. We apply SIGStat to arrays related to matrix layout and the data mapping. This quantifies matrix irregularity and load balance. They are crucial factors that affect program design choices. For the kernel state, we record the previous predicted actions, which provide a compact summary of the code generated so far. Finally, we also introduce basic matrix features from traditional autotuners. Now, let's look at the offline phase. To address the massive data collection overhead, we adopt a multi-stage self-training approach. This process runs in several stages, with each stage processing 500 matrices, and we train our model between stages. We started with the seedling stage, which is heuristical strategy to collect initial data. Then we enter bootstrapping stage, which we use these newly trained models to directly generate ground truth data for the next 500 matrices, which saves search time. However, these are early models acting as students might make mistakes. As you can see on the right side, blinding trusting the student's prediction might take the wrong path in yellow. To prevent this, we introduced a monitor as an error correction mechanism. It evaluates the student's confidence. If the confidence is low, the monitor expands the exploration range, shows as the red section, to safely captures the real ground truth in blue. Due to time limits, we are only highlighting the overall mechanism. For the details behind this, please refer to our paper. For evaluation, we use 115 matrices from the suit sparse matrix collection. The baseline are SOTA Huimin designed programs, autotuners, and sparse compiler. The performance evaluation shows that the SparseZETA achieves higher performance compared to all baselines, especially alpha sparse, which is the best baseline sharing the same search space. We think the main reason is that alpha sparse relies on ragged human-crafted rules, which is error-prone. In contrast, machine learning-based method of SparseZETA can capture the complex relation between matrix features and program design decisions. In terms of the inference time, SparseZETA reduced the search time from hours to milliseconds. This result shows the advancement of our one-pass inference. As you can see, the left side is alpha sparse. It takes over hours, but the right side is SparseZETA, which just takes milliseconds. That's conclude my presentation on SparseZETA. Thank you all so much for your time and attention today. Because of the visa issue, the first author cannot join there, and because some family issue, the last author, the corresponding author, cannot join as well. So I'm the middle one. So I will try my best to answer any questions from you, and if I cannot, I will forward them to the corresponding answer. Yeah.
Thank you. Yeah, let's take some questions. All right, well, folks, I don't think I see any hands right now. While folks are thinking about it, so a question I had is your last graph that sort of compares sparse, alpha sparse and SparseZETA.
Yep.
Am I understanding right that part of the differences is that in SparseZETA, you've done this kind of offline phase where you've collected a knowledge base, and that is a little bit costly.
Yeah.
But then you can query that knowledge base very efficiently here, basically.
For alpha sparse, you need to do iterative tuning.
Mm-hmm.
Yeah, you need one per file and then go back to the compile and do again, and that's pretty time consuming. And another important thing is alpha sparse is a human guided one, so it can be easily biased. Mm-hmm. So that's why SparseZETA get a much higher performance comparing to alpha sparse.
Very cool.
Yep.
All right, any other questions? I mean, I have more. I think this work is incredible. I think there's so many moving parts and auto-tuning versus learning. What is kind of the search space here? Because I mean, I think a big thesis of this paper is that you don't do auto-tuning. How big is that search space? It must be big if alpha sparse.
we have 24 operators in that search space, so the combination can be very huge.
I see.
Yeah.
And the question to sort of build off of that too, though, is SparseZETA is sort of like a one-time thing. It gets you a good implementation. Did you ever think that maybe that's a good seed, and then you could search around it in case your cost model found something a little bit different?
For the overall optimal setting, I would say alpha sparse might be the suboptimal, but it's comparable. Mm-hmm. Yeah, you might get 100 or 1% or 2% difference comparing to the optimal one, but to limit the search space and the time, you need to make choice between them. You need trade off between the accuracy and the search time.
Yep, the classic trade-off. All right, any other questions? If not, let's thank our speaker one more time.
Yeah, thank you.